to the third live session in this Introduction to Photonics course. So it's been going very well, I suppose, just based on the feedback that we have been getting. There's a lot of people that are following the course and doing all the assignments regularly. So that's great to see. Just keep continuing that. One thing I want to actually bring up before we go into specific questions is about this final exam. As I mentioned in the last live session, the final exam is going to be a mix of objective type questions, multiple choice questions, as well as fill up the blank type of questions. The reason is, of course, multiple choice questions are easier to offer when you are just looking at conceptual type understanding. But if you want to really see if somebody is understanding, if they are able to solve problems, it's much better to get into numerical type answers. And in those numerical type answers, we prefer that you do fill up the blanks. So what we started with in our assignments is primarily multiple choice questions, but as we moved on, we realized that we are going to go deeper into the engineering part of the course, and with that, in the last few assignments, you have seen that there have been fill up the blank type of questions. So I can tell you a little bit about the final exam now. I think it's going to be something like 10 multiple choice questions, and then several other questions that are going to be fill up the blanks. The multiple choice questions are roughly going to be 30% of your grade, whereas the fill up the blanks type of questions are going to be 70% of the grade. So if you notice in the recent assignments, we've been actually providing you more practice in fill up the blank type of questions, and that is with the objective of preparing you for the final exam. And specifically, if you look at assignment 7 is typical of the questions that you can expect in the final exam. And just to give you the feel of a final exam, maybe in your regular assignments, you've been doing this collectively. I know there are colleges where en masse there are several tens or dozens of people taking this course, and I am told that in those sort of environments, the students actually view the lectures together, which is great. So you could have nice conversations about some of these concepts even while you're viewing the lectures. But I also learned that when it comes to doing the assignments, people tend to do it together. Now, that may help you just to do the assignments well, but when you're going into the final exam, each one of you is going to be doing the exam separately. You're not going to be obviously allowed to discuss with each other. And what I had asked you to do in assignment 7 is that you simulate the final exam environment and try to handle all these questions on an individual basis without actually referring to your notes. I sent you a message across and asked you specifically to prepare the material from the first 5 assignments, review all those assignments, review all those concepts, and prepare yourself to answer questions without going back and referring to the material. And I also wanted you to do that in a time-bound manner, I was suggesting maybe 1 hour time for doing those questions. And I'm not quite sure how many of you did that. But if I go back and look at some of the statistics of the course, I am a little worried. A little worried in the sense that, let me just share you some of these statistics so you can see this on your screen now. So this is actually the average score that you've been getting across the several weeks. And for example, if you see week 7, which is what I've been talking about just now, there is a healthy average of 60%. So I'm not too bothered by that. I'm actually quite enthused by that, because that means you're able to do these problems reasonably well. But now if I scroll down, I can scroll down. Right. So if I scroll down and I look at the number of submissions, this is also great. Some 500 plus people are submitting these assignments on a consistent basis. So that is also okay. But if I scroll down further, I get to see these pillars, these large pillars. And then there is actually dispersion of scores. So I suspect that these pillars, these largish pillars, represent a collection of students doing these assignments together, right? And maybe you're discussing with each other also. So this is actually not going to help you in the final exam, especially if you look at assignment 7. You see a large proportion of people having gotten similar sort of scores, which may be, I'm not sure absolutely, but which may be representing students discussing with each other while doing this assignment. And I would say that is not a very healthy trend. So I'm going to give you one more chance. So you have assignment 7, and then assignment 8 is, I think, open right now. So people are already starting to do assignment 8. And then we'll go to 9. And then when we come to assignment 10, what we're going to have is once again another sample quiz type of paper. So you will be once again encouraged to do that sample quiz paper, which is going to be based on concepts that we have covered since assignment 5. So 6, 7, 8, 9, whatever the concepts we covered in those assignments, we will present as a sample quiz in assignment 10. So I'm going to ask you to once again, try to take that up as once again simulate as if you're taking the final exam, and do that properly, so that you have a better practice as far as dealing with the problems in the final exams concerned. Okay. So just one more thing. The other part of it is the weekly feedback that I've been getting. And I'm really glad that I'm getting feedback from people. So it certainly gives us a sense of where we are in the course and where we want to go. And I want to specifically look at week 8 feedback. So this is actually we got 19 responses. So I'm thankful for these 19 people that responded, but I'm not happy that this is representing supposedly 2,700 people that have enrolled in this course. So essentially what it means is most of you are not being heard, and I'm not sure if that's a really good thing. But of the people that have responded, I'll just quickly go through it. For example, if you look at the difficulty level of assignment, 70% or more than 2/3 are actually saying that the assignment is easier than expected, right? So I'm actually quite happy to see that. I don't want to really, if somebody had said it's much tougher than, or if there's a significant percentage of people that are enrolled who say that the assignment is much tougher than expected, I would be worried, right? But here you say the difficulty level of assignment, it's easier than expected. But then I go back and read some of these, comments. What the comments actually tell is that the questions are actually not so straightforward. They require quite a bit of thinking to do the assignments properly. And there are also comments such as this is not actually based on the video lectures. So this is actually representing, this is out of whatever lecture material that is covered and so on. So I want to go back to the video screen. So just bear with me for a moment. Right. So so what we are saying is, so this specific comment about the problems are not consistent with the video lectures, I would like to get whoever is making those comments to come up and give me an example, because this is actually material that has been developed over several years, and you rest assured you can also say that it's been actually several exams have been conducted based on this material. And this sort of a comment that the material does not represent the lectures is not typical, right? In fact, I have not heard that before. So I'm a little surprised that people say that it's not consistent with the video lectures, and maybe that is true. I'm not sure. Maybe I missed something here. But it would really help if people are being more specific about that comment. If they can actually come back and tell that, this particular question that you asked, you did not provide enough information in the lectures. So that is something I would like to hear. Okay. So please do try to be a little more specific in your feedback. Okay, that will certainly help us address that particular issue. In general, I would want to say that this is a 12-week course, and this 12-week course is in the IIT credit system. It corresponds to 3 credits. Which means that there are 3 lectures every week, and it is also expected that the students beyond these lectures spend 3 multiplied by 2, at least 6 hours of time outside of these lectures to understand the concepts and also try to answer these assignment questions and all that. So I am not sure if that is happening either. Of course, there was one isolated case where somebody said they spent 10 hours working out one particular assignment. But in that case, I would like to understand why it took that much time. In general, you just keep this as a as sort of a metric. If you are taking this course, you are expected to put in about 6 hours of work in trying to solve these assignment problems. So if you're not putting that time and you're finding the assignment being difficult, I can understand that, and I can only advise you to try to spend a little more time for the course before you attempt all the assignment problems. On the other hand, like I said, if you say that I'm spending 6 hours or more and I'm still not able to do the assignments properly, please participate in the discussion forum. Or if you are if you don't want this to be a common dialogue, maybe you can write to one of us, and then we can try to answer that. But that is, of course, if 2,700 people start writing to me, I'm not going to be able to respond to everyone. So I'm just suggesting that try as much as possible to put it up in the discussion forum. But if some conversation starts becoming very specific, we may want to take that conversation offline. Okay, so that's all the things that I had to say. So just keep plugging away and try to keep giving us feedback as we move on. Okay, now let me try to address some of the questions that are showing up here. So one question is about semiconductor lasers. So in semiconductor lasers, does the tunneling effect affect the lasing property? Okay, so that is one question that has come, and I'm actually not quite sure where that question came from, because tunneling is not a property that we had discussed as far as our lectures are concerned. So that's actually a quantum phenomena which is not very well quantified in the kind of concepts that we covered. So I'm afraid I'm not going to be able to give you a direct answer, but I can clearly say that we are actually trying to get all the carriers to come together, electrons and holes. They're all going to be we are trying to go to a double heterostructure as far as lasers are concerned, so that the electrons and holes can be confined within one particular layer called the active layer, where they have the maximum possibility of recombining and providing emission. Now, if we say there is some tunneling effect happening, we would say that there is electrons and holes are escaping that potential well that we have created in the structure, and because of that, the efficiency will go down. I'm not sure if that is what is being asked as far as this particular question is concerned, but I would say in a sort of hand-waving manner, that is what's going to happen. So then there's a question on quantum efficiency of the semiconductor, both in terms of internal quantum efficiency and then external quantum efficiency. For that, I would like to use the notepad here, if I can do that. Okay, let me see how this works. So we talk about internal and external quantum efficiency. Let me first talk about internal quantum efficiency. Internal quantum efficiency is defined as the radiative rate divided by the total, that's a radiative recombination rate, divided by the total recombination rate. Okay, and we know that the radiative recombination rate is proportional or inversely proportional to the radiative recombination lifetime. And similarly, if you write for the denominator also, that's going to be 1 over tau radiative plus 1 over tau non-radiative. Okay, which if you work out the math is going to come as tau nr divided by tau r plus tau nr, right? So that is what we call as the internal quantum efficiency. So what do we mean by that? We are saying if the recombination, the radiative recombination events happen faster compared to the non-radiative recombination events, then tau r, if it's is much smaller compared to tau nr, and in that case you have an internal quantum efficiency which tends towards 1 unity. Okay, so that's the maximum quantum efficiency that you can get. And so clearly that is what is preferred as far as light emission is concerned. So we are trying to work towards or engineer your structure such that tau r is much less than tau nr. And how do we exactly engineer the structure? That is actually through this double heterostructure. So if I were to draw the p-n junction, right, it's going to look something like this. So you have a p-type and an n-type semiconductor, and then you have this active region which typically has a lower band gap energy compared to the p and n region. So you essentially have these holes that are injected from the p region and electrons that are injected from the n region, and they actually come to the active region, which is actually lower band gap energy material. So they essentially are confined within that material, and under that confined condition there is a large probability that the recombination will happen. And once that recombination happens, the light is actually guided along this, and then the light actually comes out of the structure from that active region. Okay, so key point is tau r should be far less than tau nr for eta I to go to 1, and that is actually ensured or that is actually helped by going for this double heterostructure. Okay, so that's actually a common structure that you have for all light emitting devices. Okay, so that is about internal quantum efficiency. Now, what do we mean by external quantum efficiency? You have injected all these carriers into the active region, and you have generated these recombination events, and you have all these photons that are generated from here. Now, these photons, if they are just spontaneously emitted, all those photons are actually going in all possible directions, right? So they're all going in all possible directions. But the photons that are going along this active region, the refractive index structure tends to be something like this. So this is actually the refractive index of the of this double heterostructure, refractive index profile of this double heterostructure. So the refractive index is maximum or is greater in the active region compared to the surrounding region. So the photons are actually confined within that active region. And now the question is, how many of those photons actually go to the external medium. This is typically air. So how much of these photons escape to this external medium? That is what we are calling as eta external, right? So eta external refers to the fraction of photons which are actually escaping this semiconductor structure. Okay, so you may have a billion photons that are generated within the structure, but only a fraction of those photons are escaping the structure. Why is that? Well, that is because of the fact that if you consider this interface, if you just blow up this particular point over here, if you just blow that up, you have a scenario like this where your spontaneous emission happens in all possible directions, right? But when it comes here, it has to actually be within a cone of angles uh, where it can still escape the medium. Or in other words, if the angle is, let's say this photon is incident over here at an angle theta which is greater than the critical angle for this particular interface, then light is actually just reflected back into the structure. So it's not actually emitted. And once that reflection happens, it may be actually absorbed within the structure itself. So essentially that light does not go to the external medium, and that is why we have an eta external which is typically less than 1. Okay, only a fraction of those photons escape. Now there have been in our lectures we have seen that fraction could be fairly low because of the fact that you have a medium with a very high refractive index, and we saw that fraction could be as small as a few percent, and that is not a good situation. So if you want to actually frustrate this total internal reflection, what you typically do is you just corrugate, or you just create some surface roughness at that interface, and with that surface roughness you essentially can frustrate the total internal reflection, and thereby you can extract more photons from the structure, and you can essentially have your external quantum efficiency increase because of that. So hopefully that answers the question. Then there is a question as to, in edge emitting LED, does the edge diffraction come into play? Okay, so that's a good question. So what does edge diffraction mean? Now, if I were to extend the structure into the third dimension, and I look at this structure, now I have essentially emission from the edge facet over here. So I'm actually getting emission from here. Let me just try to show that in a different color. If I am looking at the emission in the vertical direction, the thickness of this active region is only in the order of a few microns. So if you have such a small thickness, then you tend to actually diverge. If it's a smaller the aperture, more will be the divergence of light coming from that. Whereas in the horizontal direction, there is not as much of confinement that's happening. So in the horizontal direction, it doesn't tend to diverge as much. Okay, so it will not it won't diffract as much. So you will essentially see that the total beam that you get in the far field is actually elliptical in nature. And that's because of the fact that the divergence in the vertical direction is greater than the divergence in the horizontal direction. So most edge emitting light sources will have essentially an elliptical beam coming out. Okay, so that's the role of edge diffraction as far as the emission characteristic are concerned. And then another question is, what happens to the phonons that are emitted in the indirect band gap semiconductor? So phonons are essentially vibration modes in the material. So if you have an indirect band gap semiconductor, we said any transition from the conduction band to the valence band would have to be associated with the help of a phonon. It has to be aided by a phonon, and phonon is essentially a vibrational mode. So essentially, it generates that vibrational mode which gets damped within the structure, so that energy is essentially lost. So that the phonons are not emitted, phonons are generated within the medium, and those phonons are heavily damped within the structure itself, so you don't get to observe it outside. And then there is a question which once again I don't think is quite related to what we are talking about. The question is more about Sonnet SDH. So let me just come back to this. Stop sharing. So just come back to the broadcast. Briefly explain the difference between Sonnet and SDH. And that again, I said, is not something that we are dealing with in the course. I'm not an optical networking person, so I'm not really qualified to answer that. But there's not a whole lot of difference. Both are talking about synchronous optical networking. Sonnet is a standard that's followed in the US, and SDH is a standard that's followed elsewhere in the world. But there's not a whole lot of difference between them. Okay, so that is what we have as questions. And then let me see, there are several comments. I thought there was one more question on let's see if I can go to that. There was one more question on, if I can explain what was happening in. So let me go back and share this. Okay, so there was a request to explain the solution for this particular problem that we asked in assignment 7, and that was relating to a Fabry-Perot filter, which is essentially based on a Fabry-Perot interferometer. So what we asked in this question is, can you design a Fabry-Perot filter that can essentially resolve two frequency components, which are mu1 and mu2, which are spaced about 100 gigahertz apart. And we are also told that the Fabry-Perot interferometer has a free spectral range corresponding to 80 nanometers, around 1550 nanometer wavelength. So I draw your attention to this picture over here. So this is a picture of a Fabry-Perot interferometer, basically two mirrors having different reflectivities, potentially R1 and R2. But in our case, we are considering both of them to have the same reflectivity R. So when you have an interferometer like this, it basically the wave inside goes through multiple round trips, and when they come to one of these interfaces, they either constructively or destructively interfere. And if they constructively interfere, then that's the light that gets to escape from this cavity. And that's what we are showing over here. This is intensity as a function of frequency. Only specific range of frequencies are actually meeting this constructive interference condition, and only those frequencies are going out. Now, what we have been told is that the free spectral range of this filter is 80 nanometers. So what we can say is between two consecutive peaks or consecutive frequencies that go through this constructive interference condition, the spacing is 10 terahertz. 10 terahertz is representing essentially 80 nanometers. Just to give you a feel, at 1550 nanometers, if you calculate, 0.8 nanometer corresponds to 100 gigahertz. So if you are talking about 80 nanometer, that corresponds to 10 terahertz. And then we are also told that this filter needs to be resolving two components that are 100 gigahertz apart. So you can basically say that each of these peaks should be less than 100 gigahertz, so that you can clearly resolve two frequencies that are 100 gigahertz apart. But in the limiting condition, you can take it such that the full width half maximum of each of these peaks is 100 gigahertz, right? So this is at nu 1, and if you want to go to nu 2, you just tune the filter, you just maybe change the position of one of the mirrors, and then this peak will shift so that nu 2 is transmitted. So that's how you would resolve the two frequencies. And if you say that the FWHM, the maximum FWHM can be up to 100 gigahertz, then we can define finesse. Finesse is defined as the free spectral range divided by the FWHM width. Okay, so in this case, FSR corresponds to 10 terahertz and FWHM corresponds to 100 gigahertz. So we are talking about a finesse of 100. And if you work backwards, finesse is actually defined by this expression, where R is the reflectivity of the mirror. So larger the mirror reflectivity, larger will be the finesse. That's what this is representing. So if you plug 100 back into this and do a little bit of manipulation, you will find that the reflectivity is approximately 97%. So essentially that's what we are saying. If you have two mirrors with reflectivity 97%, it will exhibit a finesse of 100, which if you say the free spectral range corresponds to 80 nanometers, will be allowing you to resolve two frequencies that are 100 gigahertz apart. Okay, and then of course the cavity length you can figure out by using this formula which we derived in the lectures. The FSR is given by C over 2 times N times L, but in this particular case, N is equal to 1 because we have been asked to assume the medium between the two mirrors is air, right? So from that you can get your L, and then you've also been asked to figure out what is the number of layers that are required. This again is something that we discussed in the class before in the lectures. So if you have alternating layers of high and low refractive index material, then you can actually make a dielectric stack, and we actually had a formula that was defined, which defined for the reflectivity of such a dielectric stack with respect to the number of pairs that are required. And using that formula, you can come up with N equal to 4. Now that is typically a formula that I would give. And this is once again to bring your attention how it's going to happen in the final exam. The final exam is actually a closed book exam, and there are certain things like, for example, that the finesse is given by FSR over FWHM. These are some concepts that I would like you to understand, and you should be able to reproduce those concepts in the exam. So you don't expect me to give these sort of formulas out, but on the other hand, if I'm looking at a reflection coefficient or the finesse, for example, you can derive these things, but it's going to take you a lot of time. And in that case, I would actually give you the formula. So in the final exam also, you can assume that any formula like this, which is not you're not able to get that from first level concepts, those formulas you can expect me to give you, so that you can use those formulas and solve that problem. So essentially, as far as this question is concerned, R is 96.6%. So you plug that in, and NH and NL are given. And once you have that, you solve iteratively, and you will find that n is actually coming to a number of 4. And n, mind you, has to be an integer value. It corresponds to the number of layers. So don't give me answers like 3.5 or 4.2 or whatever. It doesn't make sense. It has to be an integral value. Okay, so those are the questions that we had sent over email previously. Now I'll try to answer all the questions that have come live during this session. So there is actually what type of question in final exam. So maybe I should stop share here and then go to broadcast mode. Okay, so you can see me. So I'm just reading off the screen here. So what type of question in final exam? That's what we went through, whatever you saw in assignment 7 and what you're going to be once again seeing in assignment 10. Those are the type of questions that you can expect in the final exam. And like I said, I will provide you any useful formulae you need for solving the problems. How many assignments for final consideration? I think it was mentioned right up front that you will be given a total of 12 assignments, and the best 8 out of those 12 assignments is what is being considered, and that's going to carry 25% of your grade. Okay. So question from Sonali. Sonali was a former student here. Hi, Sonali. So the question is, the formula for external quantum efficiency of gallium arsenide different from that mentioned during lecture. Whatever we derived in the lecture is for any material. So it is not specific to gallium arsenide or silicon or in indium gallium arsenide and so on. So that holds good for any material. But somebody did bring to my attention that the formula that's given in the GP Agrawal is actually a factor of 2 smaller compared to the formula that we derived in our classroom. And so there was some clarification that was required. And if I can go back to that, let me see. So I think we derived this formula to be eta external equals to 2 over n multiplied by n plus 1 the whole square. And in GP Agarwal, somebody brought to my attention that it's mentioned as 1 over n into n plus 1 the whole square. So they were wondering, why is there a difference in the formula? GP Agarwal actually does this integration for angles from 0 to theta c, which is actually only on one side, the reflection on one side of this interface. Like in this case, so we are talking about reflection from. So this will be corresponding to 0 degrees, and this will correspond to theta c. So we are considering integration over only one side, whereas in our case we actually considered from minus theta c to theta c, or in other words, we actually had this factor of 2 come into the picture. So 2 times 0 to theta c, because whatever happens in the upper half can happen in the lower half also. And I think that is probably where there was a difference in the formula. But I would certainly go by what I derived in the class. So you just stick to this formula. Okay, so let me come back. Stop sharing. So just come back here. Let's see. We are unable to get the. So I'm not sure what that question about. It's about some credit transfer. Unfortunately, I am not the right person to ask about that. You can ask the NPTEL team, and they can probably tell you about credit transfer. But there's some question about. Oh, okay, I get it. So this is Meghna saying that we should give all objective type questions. Meghna, that is actually something that we discussed at the beginning of the session. That is not going to be possible as far as this course is concerned. Like I said, objective type questions are asked whenever I am expecting some conceptual understanding. But I'm actually, as I mentioned in the learning objectives of the course, I'm actually training you guys to engineer a solution for these photonics problems. It's not just a course which is teaching you concepts, but we are also trying to, based on these concepts, engineer solutions. And when you talk about engineering solutions, unfortunately, objective questions do not do complete justice to what we want to achieve. So you are going to be, tested with fill up the blank type of questions, which hopefully we are giving you enough practice. If you think you want more of those questions, let us know, and we can actually give all the questions as fill up the blank type of questions, so that you are better prepared for the final exam. As I mentioned earlier, once again, the final exam will have 70% of the questions as fill up the blank type of questions. So please do practice those questions well and make sure you're comfortable with that. And I think that's all the questions we have. Okay. There was one more question about steady state density from Sonali. Sonali, I gather that you are asking about the number density of atoms in the picture that we were talking about as far as a laser is concerned. So what we mean by steady state is, whenever we pump, maybe I can use the tablet here to explain this. So let me go to a fresh page. So we are talking about, for example, a laser system, a 3-level laser system where we pump, we provide some external energy, which is taking an ion from a ground state to a higher energy level, and maybe you have a non-radiative relaxation, and then this is where you are emitting a photon. If a photon comes up with the same energy, then you can actually have stimulated emission happening. Now, in this picture, if you are tracking, we said, if you say this is N1, this is N2, and this is N3, these are the number densities for at these different energy levels. We said this higher energy level is typically short-lived, as in the case of erbium, that energy level has a very low lifetime. So N3 is typically negligible. So we are essentially talking about the atoms are either in the excited state or in the ground state. So you have either N2 or N1 representing the total number of atoms. If there was no pump going into the system at time 0, let's say this is actually the pump power as a function of time. So if there was no pump, and then suddenly you turn on the pump, and it goes up like this, it goes up to a certain power level, let's say 1 watt. Okay, in this sort of a scenario, how does the system respond to that? The system initially responds by let's say now we are tracking N2, right? So in the same axis, let me track N2. N2 is actually 0 when the pump is 0. But when it actually suddenly gets excited, when all these photons, pump photons come in, you start having that N2 increase, right? It will increase to a certain value, and then it will start decreasing. Why does it decrease? Because it starts emitting some photons spontaneously after a certain time, and then as those photons are emitted, those atoms are coming to the ground state, but they are still getting pumped, so they will actually go up again, and then it will come down, and then it will finally reach a constant value, okay, after some time. Now this condition where it reaches a constant value is what we are calling as the steady state condition, and this condition where things are changing is called the transient condition. So for all the discussion that we had in the as far as this course is concerned, we were talking about the steady state condition, because in the steady state condition you can just say dN over dt equal to 0. Okay, that makes our discussion much simpler. If you want to capture what is happening in the transition condition, then in that case, for the transient, dN over dt, you cannot make it 0. You have to actually find the time-dependent solutions for the atomic density. So that is a little more complicated. So just to simplify things, I mean, if you really have to do it, for example, when you're talking about mode locking a laser where you're generating short pulses, you have to essentially consider the transient picture. But if you are considering an optical amplifier type of scenario, you are typically having a steady stream of photons coming in, which need to be amplified, and there is a steady stream of pump photons that are available to excite the erbium ions if you're considering a erbium doped fiber amplifier. And in those sort of scenarios, it's enough to just consider the steady state picture. So dN over dt is 0 in those cases. Okay, so hopefully that answers the questions. And I don't see any more questions here. Hopefully I have addressed all the questions both here as well as the discussion forum. But like I said at the beginning of this, let me just come back to the video. So like I said in the beginning of this session, please keep those questions coming. But what I want to discourage is generic questions like make things easier or give me it's taking too much time for me to do these assignments and things like that. Instead of being generic like that, it would help if you are actually giving specific comments so that we can go back and relate to the specific issue that you are bringing up and try to address that as well as possible. Okay, so with that, let me close this session and wish you good luck for the upcoming assignments. And if necessary, we will meet once again before the final exam, so I can hold a live session maybe in 2 to 3 weeks' time. And we'll post that information through our discussion group. Okay, good luck. Thank you.